Today I want to talk to you about optimization, which is IB subtopic 7.6. And I've got an IB problem here from paper 2 that I'd like to show you. A shipping container is to be made with 6 rectangular faces as shown in the diagram, the length of 2x, a width of x, and a height of y. All the measurements are in meters. The total length of the 12 edges is 48 meters. Show that y equals 12 minus 3x. The key piece of information is right here. The total of all 12 edges is 48 meters. What I can do with that information is I can say, all right, how many edges do I have? I've got 4 of those 2x's. I've got 4 of the x's. And I've got 4 of the y's. And I happen to know when I add those all together that it equals 48. I'm going to go ahead and solve this equation for y. I've got 8 x's here and 4 there. So that's 12x plus 4y equals 48. And I want to get it in this form. So I'm going to subtract that 12x over. I'm going to say that 4y equals 48 minus 12x. And then, of course, to get y by itself, I'm going to divide everything by 4 to get y equals 12 minus 3x, which is wonderful, because that's what I was supposed to be showing there. Next, I'm supposed to show that the volume, V, meters cubed, of the container is given by V equals 24x squared minus 6x cubed. Well, the first thing you ought to ask yourself is how do you find the volume of a box? And the answer is length times width times height, and we're given those 3 things. So I'm going to simply take the 3 things I've got and multiply them together. X times 2x times y. But you may notice that I know what y is now. It's 12 minus 3x. And say v equals x times 2x times, in parentheses, 12 minus 3x. And I'm just going to simplify that so that I can show that the volume is 24x squared minus 6x. I'm going to multiply these together first to make that 2x squared. So volume equals 2x squared times 12 minus 3x. And then I'm going to distribute this 2x squared to both the 12 and the 3x. So 2x squared times 12 is 24x squared, and 2x squared times negative 3x is negative 6x cubed. Again, showing what I'm supposed to be showing. So I've got this volume function, and they want me to find the first derivative, the derivative of volume with respect to x. And that's pretty simple. It's simply 2 times 24 is 48x, and 3 times negative 6 is negative 18x squared. So there's my derivative function. Moving on to part D, we're supposed to find the value of x for which v is a maximum. Let me just write down that derivative function again, which is the gradient function. And that is 48x minus 18x squared. The local minimums and maximums always occur where that gradient function equals 0. So I'm going to take that gradient function and just set it equal to 0. 0 equals 48x minus 18x squared. Another way to remember that is that local maximums and minimums only occur when the gradient equals 0, so you just set that gradient equal to 0. So we need to solve this thing for x, and this is a quadratic, and we've got a lot of different ways to solve quadratics, but I happen to like to solve these things on the calculator. So what I always do is I set this side equal, this is all y1 here, and then this stuff right here, that's all y2. So that's what I'm going to do in the calculator. Go into my calculator, type in 0 for y1, type in 48x minus 18x squared into y2, and I just want to see where these two things intersect, because that is the solution. Those are the probably going to be at least 1, maybe 2. I'm going to see if I can see where they intersect, and right now I'm only seeing right there. I'm just going to zoom out a little bit and see if I can see both of them. I want to see the whole parabola. Let's just set it to negative 20, 10, let's go by 5s. There's one right there, it looks like it's at 0, and there's one right here that I also, obviously 0 is not the solution because we can't have a value of x at 0. That would make the box with a length and width of 0, so that doesn't make any sense. So whatever this one is right here, that's the one we want. That's the value of x. So I'm going to do second trace 5 to find the intersection. And I'm going to move my spider pretty close to that point. And I'm going to get a value of x, which is 2.6 repeating decimal like that. As a fraction, that's just 8 over 3. See? So that's my value of x. Find the maximum, oh, sorry, I should also say that if you're going to round that, you should write x is 2.67 because that's to 3 significant figures. Part E here, we're going to find the maximum volume of the container. So all we need to do is we need to plug this 8 over 3 into the volume function, which we already have defined. So that's going to be 24 times 8 over 3 squared minus 6 times 8 over 3 cubed. And that's just calculator work. So that maximum volume is going to be 24 times 8 over 3 squared minus 6 times 8 over 3, and cubed is just math 3. And so to 3 significant figures, that's 56.9 meters cubed for the maximum volume. In part F, we're supposed to find the length and the height of the container for which the volume is a maximum. Okay, so the length and the height, I know that the length is 2x, and the height was, we showed it to be 12 minus 3x. So the length is just 2 times 8 over 3. And the height is 12 minus 3 times 8 over 3. This would be 16 over 3. And to 3 significant figures, that is 5.33 meters. And 3 times 8 over 3 is just 8. 12 minus 8 is 4 meters. So it looks like we've only got one question left, and it's a doozy. The shipping container is to be painted. 1 liter of paint covers an area of 15 millimeters squared. Paint comes in tins containing 4 liters. Calculate the number of tins required to paint the shipping container. Well, what sucks about this problem, excuse my French, is that we've been dealing with volume for the last 1, 2, 3, 4, 5, 6 parts. So part 7, they ask us a question about paint, which of course isn't volume, that's surface area. So now we got to shift gears and we got to talk about the surface area of this thing. Well, the surface area is just going to be the two faces, which are x times 2x, plus the two faces, which are 2x times y, plus the two faces, which are x times y. I'm going to use this to find the total surface area now. So I know that the x was 8 over 3 times 16 over 3 plus 2 times 16 over 3 times my y, which is the height, which we showed as 4, plus 2 times 8 over 3 times the height, which is 4. And that's a bunch of calculator work, so let's do it. Let's push this up. So 2 times 8 over 3 times 16 over 3 plus 2 times 16 over 3 times 4 plus 2 times 8 over 3 times 4 The total surface area of this thing is, let's call it 92.4 meters squared. And that beats the 3 significant figures. So that just tells me the total surface area. That doesn't even answer the question. The question was, how many tins do we have to use to paint the shipping container? Well, 1 liter covers 15 of those 92, and 1 liter of paint covers 15, but the tin itself has 4 liters in it. So the calculation itself is pretty simple. It's just 92.4 divided by how much surface area we can cover with 1 tin. Well, 1 liter is 15 of those 92, but 1 tin has 4 in there, so I'm going to multiply that 15 times 4. So 92.4 divided by 15 times 4 is like 1.54. So how many tins do I need to paint the entire box? The answer is 2. So all that fun work to find out that it was 2 tins. Alright, that's all the time that I have to show you. This is representative of probably the hardest optimization problem you will see, if you see it, on paper 2. Thank you for watching. We'll see you next time.